Hey, it's Chris from Space Weather Watch. In this tutorial, we're going to dive into the fascinating world of the sun using NASA's Solar Dynamics Observatory, or SDO, and discuss why solar scientists look at the sun in a variety of colors and wavelengths. To comprehend the sun's dynamic behavior and its profound influence on our solar system, scientists utilize an array of specialized wavelengths of light. Each of these wavelengths unveil distinct layers and phenomena, providing us with a profound understanding of our nearest star, and allow for space weather forecasting. Before we explore the sun through NASA's Solar Dynamics Observatory, let's dive into the remarkable mission and its capabilities. Launched on February 11, 2010, the Solar Dynamics Observatory revolutionized our understanding of the sun by capturing high-definition images and data at various wavelengths. Positioned in geosynchronous orbit around Earth, SDO continuously observes the sun from its vantage point, providing uninterrupted views of solar activity. Equipped with cutting-edge instruments, NASA's SDO meticulously monitors the sun's surface, atmosphere, and magnetic field dynamics. The heart of the SDO mission lies in its ability to capture images every 3/4 of a second, generating a wealth of data that scientists analyze to study solar phenomena in unprecedented detail. Its primary instruments include the AIA, or Atmospheric Imaging Assembly, which observes the sun in multiple ultraviolet and visible wavelengths, revealing intricate details of solar flares, coronal loops, and other phenomena. Additionally, SDO houses the Helioseismic and Magnetic Imager, or HMI, which maps the sun's magnetic field and provides insights into the internal structure and dynamics of our star. This comprehensive suite of instruments enables SDO to track solar eruptions, forecast space weather, and understand how solar activity impacts Earth and the broader solar system. Now, let's delve into all of the intricate wavelengths that SDO employs to scrutinize the sun. This is 193 angstroms, and is a wavelength that SDO uses to capture the sun's corona, a region of the solar atmosphere characterized by its incredibly high temperatures and the presence of extended magnetic fields. This wavelength also highlights hot flare plasma and the outer atmosphere of the sun known as the corona. Hot active regions, solar flares, and coronal mass ejections appear bright here, while very dark areas called coronal holes reveal places where very little radiation is emitted, but are crucial sources of solar wind particles. In these areas, the magnetic field lines are open, allowing the solar wind to stream out. The primary ion seen at this wavelength is 11 times ionized iron, and the characteristic temperature observed here is about 2.25 million degrees Fahrenheit. Moving closer to the sun's visible surface at 304 angstroms, SDO observes the chromosphere, a layer just above the photosphere, where prominences and filaments dominate the landscape. Prominences are massive, arching structures of relatively cool, dense gas that are suspended in the sun's atmosphere by magnetic fields. Prominences appear on the limb, while filaments appear as dark lines against the solar disk, and are as well cooler clouds of gas held above the sun's surface by magnetic forces. They can persist for days or weeks, changing shape as they are influenced by the sun's magnetic forces. The 304 angstrom wavelength captures these structures in vivid detail, providing crucial insights into how magnetic fields organize and control the flow of gases on the sun's surface. Studying the chromosphere helps scientists understand how solar eruptions and prominences can impact space weather around Earth, as some of these filaments can end up lifting off and destabilize. The primary ion seen here in this wavelength is singly ionized helium, and the characteristic temperature observed is about 90,000 degrees Fahrenheit. This is 211 angstroms, typically shown in purple. Here, SDO focuses on a region of the corona where temperatures soar to approximately 2 million degrees Celsius or 3.6 million degrees Fahrenheit. This wavelength is particularly useful for observing active regions of intense magnetic activity in the sun's corona. Here, solar flares and coronal mass ejections originating from these regions are prominently visible. Most importantly, however, dark areas known as coronal holes, where solar wind particles escape into space, contrast very well against the bright backgrounds of the corona. This is 131 angstroms, which is typically shown in teal. At this wavelength, SDO captures the hottest regions of the solar corona, where temperatures can reach several million degrees Celsius, or up to 18 million degrees Fahrenheit. This wavelength is crucial for observing solar flares, the most energetic events in our solar system, as well as coronal mass ejections that hurl vast amounts of solar material into space. The primary ions seen at this wavelength are 20 and 7 times ionized iron, indicative of the extreme temperatures present during solar flares and CMEs. By studying these phenomena, scientists can track the evolution of solar activity and predict space weather events that can impact Earth's technological infrastructure, as well as astronauts and magnetic fields evolve over time and how they drive solar activity. Sunspots are regions on the sun's surface where intense magnetic activity is concentrated. The complexity of these magnetic fields refers to the presence of multiple polarities, both positive and negative magnetic fields, and twisted configurations. When magnetic fields become more complex, they store more energy, and the whole sunspot region can become unstable over time. By observing changes in magnetic field strength, polarity, and complexity over time by looking at SDO imagery, researchers can forecast the likelihood of solar eruptions. Regions with highly twisted and mixed polarity magnetic fields are more prone to producing powerful solar storms that can affect space weather near Earth. Intensitygrams are another tool that provide a comprehensive view of the sun's brightness across different wavelengths. They help scientists monitor changes in solar activity and correlate them with other observations. We hope you enjoyed this detailed exploration into the sun's dynamic behavior through the lens of NASA's Solar Dynamics Observatory. By examining various wavelengths from the scorching hot 131 angstroms to the cooler 304 angstroms, SDO provides us unparalleled insights into solar phenomena like flares, prominences, and magnetic fields. These observations are crucial for understanding and forecasting space weather and its impacts on our technology and astronauts. Tune in again for more fascinating insights into our nearest star and its influence on our solar system. For further information, please visit sdo.nasa.gov. We'll see you again in the next video.